Good morning, everybody. I'm going to draw up some problems and give you guys a little bit of time to work through them, and then we will get started for the day. All right, so let's get started on these. One of the nice things about these alkene and alkyne reactions is they pretty much only ever accomplish one task. Unlike with your SN2 versus your E2, where you have to decide what you have. Anytime you see NaNH2 and an alkyne, it's just going to deprotonate it and then attack your alkyl halide here. So for this first reaction, we're always going to pull off this proton. And then do an attack on one of these haloalkanes. We're adding 3 carbons, so 1, 2, 3 here. And then from this point, we just need to know what our reagents do. So H2 and Lin-Lars. Lin-Lars is our poison catalyst. We think H2 always added Syn before, it's going to do the same thing. And with Lin-Lars, it's going to stop it in that double bond phase. So we've got 1, 2, 3 carbons. 1, 2, 3 carbons are double bond. And then another 3 carbons here. And that should get us to our final product. Taking a look at the second example, we're going to do the same thing in our first step here. We're going to pull off a proton. Do an attack on this haloalkane to add that to our triple bond system here. We'll get something that looks, so we have 1 bond and then or 1 carbon and then the 6-membered ring. So that should bring us to here. From this point, we're adding Br2 in excess, which means that we are going to tetrabrominate. So adding 4 Brs, 2 on each position of where our triple bond is. Giving us a structure that looks like this. And just to kind of double check, we can make sure we have the right number of carbons between the ring. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then our ring. So just in case you're worried you dropped a carbon or picked up one, sometimes it's good to just kind of count those out and make sure you have what you needed. Okay, last one. I'm going to erase the first example, so I have a little bit of room for the last one. Our first step here, I'll box this guy out. We're going to be doing 2 different additions. So again, NaNH2 and a haloalkane. Going to pull off an H. Attack a haloalkane. One carbon, and then our branch point here. We can rinse and repeat on the other side. So another NaNH2 gets us to another negative charge. I'm just going to redraw that haloalkane over here. It looks like a 5-membered ring. 2 carbons and an iodine. So our triple bond is going to replace that iodine. We've got 2 carbons and then our 5-membered ring. And then finally H2, just going to reduce down your triple bond to your single bond. So there are 1, 2, 3, 4, 5, 6, 7 carbons in between your ring and the end of your molecule. And that should give us this structure here. Any questions on these three before we go on to some somewhat similar material, but okay. So today we're going to do a little bit of synthesis over some of this chapter 9 material. And then we're going to cover a little, probably most of chapter 10 today. We may get through all of it. It's a pretty short chapter, so we'll kind of see where we end up. So we're going to start off by talking through some like mini synthesis problems. So I'm going to take an example. And kind of walk us through rough. Come on. Let's put one arrow. What it would take to get to a final product through the synthesis. So synthesis reactions are all about order of operations or order of reactions. If we look at this here, there's only really 2 reactions we need to do in order to do this. So looking at our starting material, and this is something you should like to do, try to figure out where my starting material fits into my product. So I have 1, 2, 3, and then this 4, 5 are on some sort of a, at this point, a triple bond. If I wanted to try to fit that into this final product here, I'm gonna throw another branch point in it, make it a little unique. This would kind of nicely outline to here. I've got 1, 2, 3, and then 4, 5. In this case, on a double bond now. So taking a look at what I have the structure. And it looks like I need to do 2 different things. One of them is going to be to create a double bond. The other one is going to be to add this alkyl group here. So if I think of reactions that I can use to get these 2, if I'm thinking about a triple bond to try to create a double bond, I'm going to put cis in parentheses here because it's not a trans double bond. I probably need to do some sort of H2 and Lindlar's. And then in order to add an alkyl group, we only know one reaction that does that. That's NaNH2 and haloalkane with that side group here. So let's talk through the reactions and let's look at what happens if we do them in one order versus the other order. So I'm going to do the reduction first. So if I was to add an H2 in Linlars, this would give me the double bond. But I'm going to run into a dead end. And the dead end is that we don't have an alkylation reaction with a double bond. We only have it with a triple bond. So if I try to throw in NaNH2, this isn't a reaction that works. This is going to lead to nothing. We only have the ability to do these calculations when we're using a triple bond here. So flipping the order of this, doing our alkylation first, while we still have that triple bond. Lets us create the skeleton of our product. If we take a look at this compared to our final product, now we have all the carbons we need. We can count those out if we want. 1, 2, 3, 4, 5, 6, 7, 8. So we've generated our skeleton. From here, all we need to do is reduce our triple bond down to a double bond, and we'll have our product. So again, we're doing the same thing as before, throwing in Linlars. And we're able to get to the actual correct product here. So this is an example of when if you do it out of order, it's just not going to work. So if we did the reduction first, we weren't able to do the alkylation versus doing the alkylation first. Let us get to our product. And as a general rule, I would say when you have these synthesis problems, I would focus on making your skeleton first, getting all your carbon-carbon bonds together, and then whatever you need to do after that is probably going to be the easiest way to go through it. So I'm going to give you guys another example, give you guys a couple minutes to try to attempt it, and then we'll talk through it together. So oops, okay, I'm going to give you guys a couple minutes to try to attempt this. My advice is try to build out the skeleton first and then try to figure out how to brominate. I'm going to give you guys till about, let's take 4 minutes, so 9:38, and then I'll check back in. The other cat's hiding under the bed. I don't know if we'll get her out today. Okay, so as I kind of hinted, we want to build the skeleton first. If you try and reduce anything, you're not going to be able to do an alkylation reaction. Like if you brominate first, or if you reduce down first, you're going to kind of shoot yourself in the foot. So we're going to start by just building out the skeleton. Let's take a look at what we have and where that fits into our product. So currently we have 5-membered ring, 1, 2, and then 3 carbons off of that. If we look at our product here, it'd be the same. So we have this 5-membered ring, 1, 2, 3. So most likely what we have is the building block for this, which means that as we look at this, we're missing these 3 carbons. So our first step should be to try to alkylate and add these 3 carbons on. I'm not erasing these circles and things. So let's throw in NaNH2 because that's our alkylation reagent. Followed by 3 carbons and some sort of haloalkane. Doesn't need to be, can be whatever, chlorine, bromine, iodine, whatever you like to use. And now if we take a look at what we have, we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have the entire carbon skeleton built out. From here, we can try to figure out how to make our brominations. So there's gonna be two different ways we can do this. Both of them work. There's not really one that's better than the other one. So one option is we can add in one equivalent of BR2. Ooh, actually, this is gonna give us a syn product, isn't it? Actually, this is gonna give us the wrong product. So if we did this and then threw in H2, because H2 is gonna add in a syn fashion. This would actually give us the wrong product here. So in order to get the right product, we are going to have to do our reduction first. So in order to get the stereochemistry we want, we're going to want this to be in a trans configuration. So adding in NaNH2, sorry, NH3 here can give us a trans double bond. Which we can then throw in Br2 correctly to get to our product. So in this blue pathway here, when we did the bromination first, because it gives us syn addition of H2, and when we add in the H2 and platinum, those BRS end up on the same side, versus if we do the reduction first, we're able to get the actual anti-product that's desired, which is this green pathway shown here. Are there any questions on this before I have you guys do a few more? How would the H2...
Can you explain why you used the NaNH3 instead of like the Lindlar's catalyst?
Oh, yes. Okay. So I'm going to erase this blue pathway. Or maybe just this top answer up here. Okay. So if we had done H2 and Lindlar's, so that gives us a cis double bond. Like so. And then from here, if we were to add in our BR2, we're out of space. This looks about correct. The problem is that it's rotational, or it's actually a diastereomer. So if we rotate around this bond to get our bond line structure to actually look like it's supposed to, what this is going to give us is this product here. Because we're flipping that over, we're flipping it 180 degrees. Anything that is a dash becomes a wedge. So when you do this reduction with Lin-Lars, you end up with just the wrong diastereomer. We have to make a trans double bond in order to get the right configuration we need down here in order to make this product, or else you end up with the same thing we had over on this H2 pathway, where they end up looking syn to each other. Does that make sense? And just to kind of go over this concept on a little bit of a simpler molecule, if I take this molecule and I literally just rotate this bond here, when I twist it into this shape, so this part will stay the same, but this bottom, when I flip it over, that went from a wedge, it'll now be a dash because I'm rotating it 180 degrees. These are the same molecules, they're just constitutional isomers. So when we're doing these reductions and we're starting with either cis or trans double bonds, when we add in Br2 and we get this anti addition of bromines, if I try to put these into the same configuration look, so if I spin this one around the bond again to make it look like the bottom molecule, it's going to rotate that dash to a wedge, and they're going to end up as diastereomers. So it's another example of where you really need to like keep the configuration you started with in your product, or else you're going to end up flipping the stereochemistry and creating diastereomers. Does that help?
Yeah, that makes sense.
Okay. So I'm going to draw up two of these, let you guys kind of work through them and try to solve them. And then we will talk through them together. So, and then probably move on to some chapter 10 stuff. Let's see. Let's do that. All right, I'm going to give you guys till about 10 to go through these. We'll go through them together, take a little break, and throw in some chapter 10 material. Let's say 57 instead. I don't think it'll take you guys that long. Yeah, I'm going to erase the bottom one, start with the top one. Okay, so we're going to need some sort of carbon skeleton for this. Most likely, we're going to be doing, I don't know, H2SO4, H2O, and mercury sulfate in order to create this. Oops. Ketone here. So if we kind of think of this a little bit backwards, if we wanted to get to here, we need something like this. So with this in mind, we can kind of use it as a template in order to make our starting material here. Or from our starting material to try to get to this is kind of like a waypoint. And then from there, we go to our final product. So we need to build out these two alkyl groups. If we add in NaNH2, and then this 2-carbon chain on the left, rinse and repeat to make the other side. And then from here, if we add in the reagent to make a ketone, these are both secondary, it's symmetrical. It's not going to really be selective for one versus the other. So hypothetically, this would make either this product or this product, but because they're just rotational isomers, these are the same. And they both get us to our final answer. There is another way you could do this where you end up with your triple bond in a slightly different spot, and then you end up with like one of the answers from this last step being correct and the other one not. But this is by far the most efficient way to do this problem. Are there any questions about this one? Okay, we got a question in the chat. So, so I think what you're asking is, what if I tried to do let's clear this. Well, I'm going to clear the top part of it. If you treated oops, this like this here, so you tried to make the entire alkylation you're adding in 4 carbons instead. you could get to here. The problem is if you try to form your ketone at this point, adding an H2SO4, H2O, mercury sulfate, is that you're going to end up with your ketone in the wrong spot. And then at this point, you guys don't know a way to move these around. There is a way you could do it if you like reduced your double bond and then, or I guess you could add in, yeah, you could add in HBr in excess. A small base. And then added in your H2SO4. That's a few more steps. Yes, and then there was a question when we get to too many carbons. Here, could you have added in BH3 THF? Because this is non-terminal, yes, that would work. So if you added in BH3 THF, H2O2, and NaOH, that'll also bring you to your final product. Because there isn't a primary one, there isn't one that's less substituted, just like there isn't one that's more substituted, both of those to give you the answer. Any more questions on this one? No, either of them's fine. You don't need to, like, there's not one that's better than the other. So as long as you have one correct pathway, you'd be fine. All right, let's go through this last one. All right, it's gonna be really hard to brominate anywhere other than when the triple bond is. So most likely, missing BR. These two carbons here where our BRs are is gonna be where our triple bond is. So doing our alkylation steps first. Getting our left half. You could do these in any order. We need 3 carbons over here, building out the right half of our molecule. This lets us build out our carbon skeleton. From this point here, looking at our product, we have syn BRs. BRs always add anti. If we look at this skeleton, it looks like it came from a trans double bond. So in order to make syn BRs, we're going to have to start from cis and then just rotate it. So if we take our material here, add an H2 and Lindlars. Or you could do this the other way. You could just throw in BR2. Actually, that's probably easier. So throwing in BR2, one equivalent. Lets us brominate here. We could then add an H2 platinum, and that's going to add sin, so that would give us this final product here. Another option is you could add in H2 and LINLARs before you brominate, and then add in BR2, and that would give you the same product. But both of these pathways would work. And often for these synthesis problems, there are two ways to do them. Okay, any questions on this one? I think this one's maybe a little more straightforward. If not, let's take about 5 minutes. So let's come back at 10:13. We'll start on some chapter 10 material. There we go. Okay. Whew. So chapter 10 is all about radical reactions. Unlike most of these chapters where we're a question on the last thing, which was how do the BR2 and the last problem add sin. So when you add H2, it always adds sin across your bonds here. So we would end up getting these H's going into the same position. So because those two are sin, it's going to make the two BR sin. Okay, chapter 10. This chapter, we're dealing with radicals. So normally when we're dealing with bases and things like that, we're pulling off protons and leaving 2 electrons behind. Let's get right a base. So this here would pick up a proton. We'd kicked out 2 electrons to this carbon position. Not H, what am I doing? Negative here. And make this negatively charged carbonium here. When we deal with radicals, we're going to be doing things a little bit differently. So something you may notice or may not notice is that we're using what are called full arrows right now. So these arrows where you have both sides of the arrowhead. Ooh, it's a little rough. This represents 2 electrons moving. Versus when we do radical reactions, we're going to use half arrows. So you notice that half of the arrowhead is missing. And this is going to correlate to 1 electron moving. Subtle, and it's kind of an odd concept, but that's what they chose. So when we're doing these hydrogen extractions with radicals, we're going to show an electron moving with a half arrow and another electron moving. So these two would come together to form a bond. The other electron from this carbon-hydrogen bond would get kicked over back to our carbon. We're going to form a radical. Radicals are neutral, so you don't need any sort of charge on them. They're highly reactive. They use these little half arrows. So stability for them is really straightforward. It's the same things we've been doing for everything else. We think of our normal carbocation stability. More substituted it is, the more stable it is. Radicals are going to operate the exact same way. Let's last when we have resonance, which is the most stable. So carbocation stability or radical stability. I should have written carbocation up here. Radical stability is going to follow the exact same pattern. So primary radical is going to be your least stable, followed by your secondary radical, followed by your tertiary radical, followed by your radical with resonance. And then the more resonance you have, the more stable it is, just like with the normal carbocation. And this one up top too. All right, so for radical reactions, our simplest one is going to be brominations. These reactions are particularly useful because you can do them when there's nothing on your molecule. So up till now, we've been doing some sort of substitution or addition to an alkyne, or, every reaction requires some sort of functional group to it. The advantage of a radical reaction is you can take just unfunctionalized carbons here, throw in something like Br2 and light, and we'll be able to functionalize them. Generally speaking, especially for brominations, these want to form the most stable radical they can before forming their product. So if we have something like this molecule where we have a bunch of different groups, we have a second or tertiary group, a secondary, and a bunch of different primaries. Our bromination is going to be highly selective for this tertiary position. The mechanism for these reactions are odd. This is really the only chapter in the book where we have these type of mechanisms. There's going to have 3 different steps to them. There's going to be a initiation, a propagation, and a termination step. So let's break down this reaction. So our initiation step. Every initiation is going to be the same. It's going to start with something that has no radicals to it. And it's going to create something that has 2 radicals. This makes sense. You're initiating your reaction, so you're creating the radicals. If we take Br2, hit it with a beam of light, I'm going to draw the light in green. It's going to split this bond in half. So 1 electron, 1/2 arrow goes to this bromine, the other electron goes to this bromine here. It's going to leave us with 2 equivalents of Br radical. Our next step is going to be what's called propagation, and this is where we're going to make our product. So propagation is really the most important step. We are both going to make our product as well as remake our starting radical through this process in order to continue doing this. Ideally, initiation only happens a couple of times, and then propagation is the cycle that runs through the entire thing. Every step in your propagation So if you looked here, we had 0 radicals. If you look here, we end up with 2 radicals. For our propagation steps, we're going to start with 1 radical on one side of our equation. And we're going to end with 1 radical on the other side of the equation. So we only have 1 radical right now. We have Br radical. If we take this in solution with our starting material, it's going to want to pull off this tertiary hydrogen. It's the most stable one. So we'll have 1 electron come from our radical, another one from our carbon-hydrogen bond. So that's going to make HBr here. And then the other electron from the bond is going to end up on the carbon here. So we're going to make HBr plus a different radical. So like we said, 1 radical over here. We're ending with 1 radical over here. In order to get to our final product, as well as keeping this cycle alive, we need to remake this Br radical to keep going. So what'll happen is our carbon radical can interact with another equivalent of our Br2. We will pull an electron from our carbon radical, 1 electron from this Br2 bond. The other electron will end up on this Br. We're going to get 1 equivalent of our product. Plus a Br radical. So over on the left, we had 1 radical. On the left, we ended up with 1 radical on the right. And then most importantly, we remade this Br radical. So this can get shoved back into the start of our cycle in order to keep doing this. The final step, I might try. Nah, I'll just wait a second. So I'll give you guys a minute to keep writing. All right, so our final step. In these radical reactions is what's called termination. It's the opposite of initiation. We're going to start with 2 radicals. We're going to end up with something that has none. So usually I'll only ever ask you guys to draw 1 termination step. So an example of this would be taking 2 equivalents of our Br radical. So each of these are 1 radical. They can come together to form a bond. That would be neutral. So it doesn't have any more radicals on it. It's called termination because at this point you would be able to keep going. This would have to get fed into initiation and then back into propagation to do anything. Another example of this termination would be Br radical plus our carbon radical. These could form an equivalent of our product. Again, we don't make any Br radical here, so we can't keep propagating the reaction. This is just a terminal step for it. Also, you can get a byproduct. Where this carbon radical interacted with itself. And you make something very messy that looks, let's see, bond there, like this. So one of the issues with radical reactions is you do get a lot of unwanted byproducts. Generally speaking, the termination products are not your main product. That's what's formed in propagation, but it tends to be a little bit messy. Okay, so these brominations are very straightforward. I'll give you guys a minute to keep writing this. They are highly selective for tertiary positions versus. Oh yeah, someone asked if stereochemistry is lost in radical reactions. Yes, there's no stereochemistry. You form a radical, you're going to completely lose your stereochem. Okay, so these are highly selective for tertiary positions, over secondary, over primary. Quaternary you can kind of ignore because there's no hydrogens to pull off. Our selectivity factor for bromination reactions is extremely high. Because Br is such a large molecule, it can handle a radical pretty well. The selectivity factor for a primary versus a secondary versus a tertiary center is a ratio of about 1 to 80 to 1600. So you're roughly 1600 times more likely to form the Br at this position than you would be at one of these primaries, and 80 times more likely than you would at one of the secondaries. So because of that, we don't even bother to do any sort of math with these. We just always assume it's going to form the tertiary position. It's almost impossible for it to form anywhere else. Chlorinations, on the other hand, are dramatically less selective. Chlorine is a much smaller molecule, which means it's a lot more reactive. That Cl radical, it has a harder time holding the radical, and it's just going to react with pretty much anything it can. Our chlorination selectivity is going to roughly be 1 to 4 to 5. And let's talk through exactly what that means. So I'm going to erase the top part of this with these BRs here and go through a couple problems where we're picking out chlorine selectivity. And as a note, the chlorine selectivity is per hydrogen. And let's just take this first example and break it down. So there's a couple things we need to take a look at when we're dealing with Cl2 and light. First thing we want to do is identify any centers that are going to be symmetrical. So for instance, this CH3 here and this CH3 here are symmetrical. They are interchangeable, it'll be the same molecule, versus the CH3 that's over here. is going to be different than those two. So because of that, we can kind of treat these like they're all the same center versus this primary center over here, which is kind of alone on an island. It doesn't have any symmetry to it, so it's just by itself. So when we're doing our math for these, the ones I circled in red, we're going to treat them like they're one center, and then we're going to treat these ones like they're a completely different center. So let's isolate how many hydrogens we have in each position and talk through that. I'm going to erase some stuff. And let's draw in some hydrogen. So we have, whoops. Six hydrogens on these primary centers. Another 3 on these 3. So like I said, we're going to treat these ones like they're just one big group here because of the symmetry to it. So the way we're going to calculate this is we're going to take the number of hydrogens times their selectivity factor. So I'm going to abbreviate it just SF. So for this here, we've got 6 hydrogens on this primary center. The selectivity factor for a primary center over here is 1. So it's going to be 6 times 1. Our other primary center has 3 hydrogens on it. Selectivity factor is still 1. The selectivity for chlorinating at this position will be 3 here. Okay, let's take a look at our secondary position. It has 2 hydrogens on it because it's a CH2, which means we have 2 hydrogens times our selectivity factor. Looking over here, that's 4. This should not be a times sign. This should be an equal sign. There we go. So this has a selectivity of 8 here. Lastly, taking a look at our tertiary center. It's only got 1 hydrogen on it, which means, so 1 hydrogen times its selectivity factor, which is 5 here. So its selectivity would be 5. We can add these all up if we want to get a rough percentage of our reaction. So 6 plus 3 is 9, plus 8 is 17, plus 5 is 22. This will give us a rough yield for our reaction. We can see that this is clearly, we could see it before we added the 22, but we can see this is clearly your major product. Going to give us the biggest number. 8 out of 22 is roughly 30%, so you can imagine these aren't great reactions. But it's going to chlorinate on this secondary position. So this reaction would actually favor this product versus the bromination which is going to dramatically favor our tertiary position. All right, let's do another one of these chlorinations, and then I'll give you guys one to do on your own, and then we'll talk through it, and then we'll be done for the day, and Thursday we'll finish up this chapter. So I'm going to take, let's see, I like this one. Make it a little better. We're in Cl2 and light. I'm just going to go through and just kind of identify what kind of centers we have. We have these primary centers here, one secondary in the middle, two tertiaries. This molecule has a lot of symmetry to it. Yellow really doesn't show up well. Go in red. There's a nice plane of symmetry here. So because of that, these two CH3s are going to be symmetrical. We're going to be able to count them the same. And then all of these, or sorry, these two CHs are going to be able to count the same. All these CH3s are also going to count the same because we have so much symmetry on this molecule. All right. So let's go through each of these, start taking an assessment of them, and then talk them together. So starting with the primary ones, all of these primaries are nicely symmetrical. We have a total of 12 hydrogens here. Our selectivity factor is still 1. So this will give us a selectivity of 12. Our secondary center in the middle, it's got 2 hydrogens on it. Its selectivity factor is 4. So it's going to have a selectivity of 8. Last one here. We've got 2 tertiary ones. So 2 times 5 for a tertiary. Gives us a selectivity of 10. So because of that, 12 is still our largest number. Technically 30 is our total. So roughly a little bit more than 1/3 product is going to be secondary or primary. And our major product for this would be chlorinating any one of these symmetrical primary centers. Is there any questions on this? Okay.
So I have quick questions.
Yeah.
I have quick questions. So the last sample, you have the primary with 6 times 1 is 6 per 22, and then 3 times 1 will be 3 per 22. So that's on of them it look like 9 hydrogen. So but we not pick that is the major product with fluorine.
Yeah, so it's the reason for that is that so this and this are the same thing, right? I'm just rotating around this bond and they become the same molecule. If I chlorinate at the other position, this is a different molecule here. My connectivity is actually different on this one, which means that these are different primary centers. So these two primary centers get treated like they're the same. This one gets treated like it's by itself. As opposed to on this example we just did, where if I chlorinate here, it's the same molecule. I just flipped it over. Same thing if I chlorinate here. And if I chlorinate here, these are all the exact same molecule. They're just rotational isomers of each other. Whereas down here, you have a completely different molecule. Does that make sense?
Yeah, thank you.
Okay. Did you have another question? No? Okay. So I'm going to draw up one of these, have you guys work through them, and then we'll go through them together and call it for the day. So let's pull, let's see. So take about 4 minutes to go through this one. I'm going to start drawing in some hydrogens while you guys do it, and then we will talk through it together. So if you get stuck, kind of look over at the example I'm drawing through, and then we will talk through them together.
I think you forgot one of the tertiary bonds.
What?
Isn't there a third tertiary one?
Oh, you're right, I missed one.
Should there be another one at the bottom as well?
We're on a room. Nope. Okay, he's getting over here. Okay, so let's break this one down. I kind of labeled them out as which ones are symmetrical. So we've got 1 and 2 in red. Sorry, 1 in red over here. Another one that's over here. These guys are symmetrical to each other. I put this 2 at the top, 3 at the bottom. So 1 has symmetry. So all 6 of those hydrogens are going to be kind of the same. We've got 2 has 3 hydrogens to it. 3 also has 3 hydrogens to it. So we can fill those ones in. 4 is also symmetrical. We got a plane of symmetry right down the middle of this. We can group these two together. We've got a total of 4 hydrogens here. So this will give us a selectivity of 16. And then we have a whole bunch of tertiary ones. So 2 of them are symmetrical. That's going to be 5. So we can group those 2 together. Give us a selectivity of 10. And then 6 and 7 should just be by themselves. Each one will have a selectivity factor of 5. So with that in mind, 16 is going to be our largest number. Means that's going to be our major product. So for this, we should get chlorinations at this secondary position, which would be position 4 on our molecule here. So someone asked why are 2 and 3 not symmetrical? So I think this chlorine is like a carbon away from these 2 versus if it's down here. In order to get to our neighboring carbons, versus 1, 2, 3, this connectivity is different. These guys have shifted, and these are just, at this point, they're just constitutional isomers. Does that make sense? Sometimes drawing out the answers makes it a little more obvious. As another thing, if you guys get stuck and you think something are symmetrical and you're not sure, typically if you draw them out, it's a lot easier to see. Okay, let's stop here for the day. I'll see you guys in recitation. We're going to do a lot of probably alkyne products today. And then on Thursday, we'll kind of finish up chapter 10 and start on some NMR. So I will see you guys a little bit later.
I have just quick question about a recitation. So as the syllabus reports, the recitation will be on Monday, Wednesday, Friday, right? On Monday, Wednesday,
Yes.
Thursday.
Someone asked the class that today because one of the classes is one Monday, Wednesday, Friday. The other one is supposed to be one Monday, Wednesday, Thursday, and I didn't realize that. So if everyone's okay with doing it on Friday, just to keep them the same, we're going to do that. But if not, we will go Thursday. So we'll resolve that at the start of recitation today.
Yeah, because I see the office hours on Thursday will be 11 to 1. So that means the recitation not on Thursday, right?
Right. If that's the case, I'll switch it and I'll do 1 hour on Thursday, 1 hour on Friday. It'll just depend on what people are able to do. So we'll resolve it at the beginning of the recitation.
So
in about an hour.
sorry, I'm not sure I understand what you mean. So finally this week the recitation will be on Thursday or will be on Friday?
It will probably be on Friday, but if it's a big conflict for people, we'll change it and it'll always be on Thursday. So We'll decide that in recitation today when people want to meet.
So that's mean this week will be on Thursday too, right?
It should be on Friday. Well, you're in the 12:05 class? Recitation?
Yeah, from 12 to 1.
Okay. Yeah, we'll talk about it at the start of the recitation.
So that's mean you will talk about that in this recitation today.
Yes.
Okay, thank you so much, Dr. Bell. Yes,
You're welcome.
thank you. Yeah, bye-bye, thank you.